This meeting is being recorded.
Section 9.6 looks at hydrohalogenation reactions of alkynes. So we can compare these reactions to the hydrohalogenation of alkenes, and we'll look at a couple of different conditions of these types of reactions. So first off, a hydrohalogenation will add a hydrogen atom and a halogen that we'll call X to an alkyne. Same as with an alkene. So we can see here first, we have an alkene, a double bond. We have a HX reagent here. So at the more substituted position, because we're told that Markovnikov addition is followed, we'll have X installed here. And then where there's more hydrogen, we know we'll have the hydrogen. So that's with an alkene, and the same thing will happen to an alkyne. So the X will go here, hydrogen there, and that's what we see. And then what results after a second addition would be at the more substituted site again, we'll have another halogen installed, and then we'll have another X over here. So the product is what we call a geminal dihalide. So on the same carbon, there are two halogens, right? So this carbon here has two halogens. So let's take a look at what's actually happening here. So if this were the mechanism in an analogous fashion to HX addition of an alkene, we would form what's called this vinylic carbocation. And this is very unstable, and therefore this mechanism is probably unlikely. This probably is not what actually happens. So we can't model an alkyne addition hydrohalogenation reaction in the same sense that we do with an alkene. So since these vinyl carbocations aren't formed, we have another way of determining a mechanism. So we have this kinetic data. So we look at reaction rates, and we find that the rate of a reaction, of course, there's our rate constant K, but this rate of this reaction is related to the concentration of the alkyne, and that's first order, we're told. So we can imagine there's an exponent of 1 here, right? And then we have our concentration of our HX, and that is second order. So this has an exponent of 2. Whenever we have something that is second order with respect to that reactant, we have to square the concentration, or in another way of saying we have an exponent of 2. So this is a termolecular process where we have 3 molecules interacting at once. So this is actually, based on the kinetic data, another proposed mechanism that is a little more plausible. So we actually have here 1, 2 molecules of our H and then our halogen, right, whatever it may be, bromine, chlorine, or iodine. And we see that this arrow here is showing addition of our X onto this side of the triple bond. And at the same time, the triple bond is acting as a nucleophile, and it's grabbing that proton there. So we have loss of a leaving group with this second arrow and this second molecule. So what we see in this transition state is that two HX molecules are interacting. So this bond is forming here, and this bond is forming here, while this bond is breaking, and this bond is breaking. So we have, in the end, an installation of X down here, and then we have this H up here. So again, we would have the more substituted position at the second HX addition across this bond. So we would end up with that geminal dihalide. when we have hydrohalogenation of alkynes and a radical reaction occurs, this happens when we have peroxides. They promote an anti-Markovnikov addition now. So instead of seeing the halogen, in this case specifically, we only have this reaction work with bromine specifically. We'll install on the least substituted position. So our bromine would go over here, and then our hydrogen will go here. And then we'll see a mixture of the E and Z, or Entgegen and Zusammen isomers, right? So we have our E here, opposite sides, Zusammen, same side. And this radical mechanism we'll look at in more detail in Chapter 10 when we study radical reactions. So as we continue here, we see that in our top forward reaction here, we have an alkyne having a hydrohalogenation addition across the triple bond of H and X to form that dihalide product. At the same time, we have the complementary, or the reverse of that reaction, seen here when we add excess sodium amide in ammonia, and then in step 2 we add an aqueous workup. So this produces our terminal alkyne again. So we'll take a look at hydration of alkynes in our next video.